Chapter 1. Zigbee. Imagine your first smart home project. You screw in a Zigbee bulb, tap your hub's Add button, and wait. Nothing happens until you press the bulb's tiny reset hole and hold your breath. That experience reflects Zigbee's design priorities. Zigbee uses a low-power mesh built on the IEEE 802.15.4 specification for sensors and simple controls, not plug-and-play appliances. Each device can relay messages. A signal hops from bulb to bulb like neighbors passing notes down a street. That self-healing mesh keeps working even when one node drops. But it also means the network crawls at around 250 kilobits per second. Zigbee radios sip energy. A door sensor can run on a coin cell for years because it sleeps most of the time. But the 2.4 GHz band Zigbee shares with Wi-Fi and Bluetooth is noisy. A busy Wi-Fi channel can drown out Zigbee whispers and add lag to your lights. You can change the Zigbee channel in your hub settings to avoid overlap. That simple tweak often improves reliability more than buying new devices. Zigbee devices organize themselves into roles. A coordinator starts the network, picks a channel, and stores the keys that secure communication. Routers, typically mains-powered bulbs and plugs, stay awake to forward traffic. Sleepy end devices attach to a router and wake occasionally to check for messages. When you unplug a router, neighboring routers recompute paths so your commands still get through. At the application level, Zigbee defines clusters, common vocabularies for lights, sensors, or thermostats. Clusters make devices interoperable, but some vendors extend them with proprietary commands. That's why a generic hub may turn a bulb on and off, but not support dynamic scenes or firmware updates. Certification guarantees basic behaviors, but not advanced features. What should you take away? Zigbee excels at connecting low-power sensors and lights throughout a home, thanks to its energy-sipping radios and self-healing mesh. Its weaknesses are low data rate and occasional interference from Wi-Fi. Before buying, make sure your devices and hub use compatible Zigbee profiles and clusters. Place router devices evenly. Choose a channel away from your Wi-Fi and avoid devices that insist on proprietary cloud connections. Get those basics right and your Zigbee devices will behave like quiet housemates, doing their job and letting you forget about the plumbing. Next up, we examine Z-Wave, another protocol that lives in the sub-gigahertz band and trades bandwidth for range and regional quirks. Chapter 2. Z-Wave. Imagine you install a Z-Wave smart lock and it just works, even when your router sits in the basement. That reliability springs from Z-Wave's use of sub-gigahertz spectrum, 908 MHz in North America, 868 MHz in Europe, where signals travel farther and through walls with less competition. Z-Wave is a proprietary protocol maintained by the Z-Wave Alliance. Certified devices speak the same base language, making interoperability easier than with Zigbee. Each network has a primary controller, usually a hub, that assigns node identifiers and security keys. Mains-powered devices act as repeaters. Battery-powered sensors sleep most of the time to conserve energy. Classic Z-Wave supports up to 232 nodes. The newer long-range extension increases both node counts and single-hop distance by using a star topology instead of mesh. Z-Wave's strengths are range and consistency. By staying below 1 GHz, Z-Wave avoids much of the congestion that plagues 2.4 GHz networks. All certified devices must implement the core command classes, standardized messages for lights, locks, sensors, and more. When you pair a Z-Wave light switch from one brand with a hub from another, the security handshake and message format are defined by the specification, so basic functions simply work. Differences emerge in advanced features. Some devices support scene control, energy monitoring, or multi-channel endpoints. Those require hub support and often proprietary extensions. Firmware updates travel slowly across the low data rate. Updating a lock can take minutes. Because the protocol is proprietary, updates and security patches depend on the single silicon vendor, Silicon Labs. There are caveats. Z-Wave radios are region-locked. A device built for Europe will not operate legally in North America, and vice versa, because the frequencies differ. Before buying, check the region code on the box. And while all certified devices speak the same language, older versions of the Z-Wave stack may not support newer security keys or command classes. Make sure your hub supports the S2 security framework and the features you need. In summary, Z-Wave is well suited to locks, garage door controllers, and sensors that need longer range and robust messaging, especially in homes with thick walls or crowded Wi-Fi channels. But its proprietary nature and regional splits mean you should plan your purchases carefully. Next, we turn to Thread and Matter, the open standards that seek to unify smart home radios under a single IP-based umbrella. Chapter 3. Thread and Matter. Thread takes the same IEEE 802.14 radio as Zigbee and builds a modern mesh that speaks Internet Protocol. Each Thread device gets an IPv6 address. Your thermostat and motion sensor can talk to your phone over your home network without going through a vendor cloud. There is no single coordinator. Instead, router nodes elect a leader and share routing duties. If one goes offline, another takes over in seconds. Sleepy end devices attach to a parent router that buffers messages while they sleep. Thread border routers, smart speakers, or access points with Thread radios connect the mesh to your Wi-Fi so your phone or laptop can discover devices. They advertise services using standard multicast DNS, so you don't need a proprietary bridge. The architecture is self-healing, secure, and designed for low power. Because Thread speaks IP, it can use standard security, like transport layer security, to encrypt messages. On top of Thread and Wi-Fi, the Connectivity Standards Alliance and major tech companies have built Matter. Matter defines how devices describe themselves and their features. A Matter-certified light bulb exposes standard attributes for on-off, brightness, and color that any Matter controller can read. During setup, you scan a QR code on the device. Your controller verifies the device's attestation certificate against a list of trusted manufacturers. If it checks out, the device is allowed onto your network. Matter runs over Thread for low-power devices and over Wi-Fi or Ethernet for high-bandwidth ones. It can also use Bluetooth Low Energy for commissioning. The goal is to let you buy a Matter bulb and use it with Apple Home, Google Home, Amazon Alexa, or an open-source controller interchangeably. Because Matter uses versioning, new features can be added over time and remain optional so older controllers still work. Mechanics are simple but powerful. Thread compresses IPv6 using 6-low WAPAN to fit into small radio frames. Each node participates in routing. Border routers announce the presence of the mesh using multicast DNS. Matter defines clusters and attributes in a common schema. Instead of each vendor inventing a new command for dim this light, there is one command with defined parameters. Devices advertise which clusters they support, and controllers can query them. Firmware updates can add new clusters or features and are delivered securely over IP. Here is the mid-synthesis across our protocols. Zigbee showed us that a mesh can connect low-power devices across a house, but suffers when profiles diverge. Z-Wave leveraged sub-gigahertz frequencies for longer range and simpler interoperability at the cost of vendor dependence and regional variations. Thread brings the mesh concept into the IP world with self-healing routing and open standards. Matter adds a universal language so your phone or speaker can talk to any device, regardless of brand, using the same verbs and adjectives. The rule of thumb emerging here is to match the protocol to the job. For battery sensors and bulbs, choose Zigbee or Thread. For locks and long-range sensors, choose Z-Wave. For devices that need high bandwidth or direct internet connectivity, Wi-Fi remains essential. Understanding these choices prevents dead batteries and laggy responses. In the next chapter, we'll unpack Wi-Fi and Bluetooth and discuss a caveat about marketing terms that obscure real capabilities. Chapter 4. Wi-Fi and Bluetooth. Before we dive into the radios you use every day, a caveat. Version numbers on the box don't tell the whole story. A product labeled Wi-Fi 6 may implement only part of the specification, or only on one band. A smart plug may claim Bluetooth support but omit the low-energy features you need for long battery life. Such mismatches create the frustrating symptoms you've probably seen: devices dropping off when you microwave popcorn, or headphones stuttering despite claimed high-fidelity codecs. The core message is to look beyond the logo and read which features are actually implemented. Wi-Fi is the workhorse for high-bandwidth devices like cameras and streaming boxes. It operates on 2.4 GHz, 5 GHz, and 6 GHz bands. The 2.4 GHz band travels farther but is crowded with Zigbee, Bluetooth, and microwaves. The 5 GHz band offers more channels and higher throughput but shorter range. Wi-Fi 6 introduced orthogonal frequency division multiple access, allowing the router to slice a channel into smaller subchannels so multiple low-rate devices can communicate simultaneously. Wi-Fi 6E opens up the 6 GHz band, providing additional spectrum with less interference. Wi-Fi 7 promises multi-link operation, bonding bands for greater throughput and lower latency. But early routers only support pieces of the evolving specification. If you need consistent high speeds for a camera or gaming rig, read the spec sheet to see which features your router and device both support. Bluetooth comes in two flavors. Classic Bluetooth streams audio and supports profiles like A2DP for stereo speakers and HSP for headsets. Bluetooth Low Energy trades bandwidth for power efficiency. Bluetooth Low Energy uses short advertising packets on the 2.4 GHz band. Devices wake, broadcast a tiny packet, then sleep again. This is why a BLE beacon can trigger a scene on your phone without draining either battery. BLE also supports mesh networking, though adoption has been modest compared to Zigbee or Thread. Newer versions add LE audio, enabling low-power shared audio streams. Interference is mitigated by adaptive frequency hopping, but heavy use of the 2.4 GHz band still creates collisions. Wi-Fi and Bluetooth coexist better when routers support coexistence algorithms that schedule transmissions around each other. Mechanics of reliability revolve around how devices schedule and prioritize packets. A microwave oven radiates noise near 2.45 GHz, blanking out channels. Concrete and metal attenuate high-frequency signals. Some smart home designers run Ethernet to powered devices like cameras to bypass wireless altogether. For battery-powered devices, Wi-Fi sensors that support power-saving modes last longer. When adding new devices, check whether your router supports the same generation and whether the device can use a less crowded band. In the Bluetooth world, look for devices that support the latest BLE versions if you care about features like LE audio. Now that we've covered the ubiquitous radios, the final chapter ties it all together with hubs and bridges, showing how to blend multiple protocols and ensure your network keeps working as new standards arrive. Chapter 5. Hubs and Bridges. The unsung hero of a smooth smart home is the hub, a device that sits near your router, listens on multiple radios, and speaks a single language to you. A Zigbee bulb only understands Zigbee. A Z-Wave lock never hears Wi-Fi. The hub bridges those languages. In the Matter era, hubs often become border routers and controllers. A thread